Hello everyone. Welcome to the fifth lecture of the series on deep learning for control. In this lecture, we will be discussing residual neural network or ResNet and its application in unsupervised model extraction. Here is the overview of this lecture. We will start with a brief introduction to residual neural network or ResNet. Then we move on to the ResNet autoencoder with ordered variants or RAEO and its application in model extraction. In general, residual networks or ResNets are neural networks that have a residual or skip connection. We can represent a residual connection as in equation 1, where we can either have a direct skip connection as shown in this figure, or we can also have a skip connection with a linear weight as shown in this figure. This we can consider as a weighted skip connection, which gives the output y as aw into x plus fnn of x. And in this case, the output y will be equal to x plus fnn of x. And this one is the most popular version of ResNet, which is commonly used in the literature. This combined block we can denote it by frn, which denotes the ResNet function. And for FNN, we can have a deep learning architecture which containing L layer. Now we have the predicted output sequence with the ResNet can be represented as in equation 2, where we have D output samples predicted using the ResNet function. And the training parameters of ResNet can be represented as in equation 3, which consists of the parameters of the neural network part, which is denoted by theta, and the weighting matrix of the skip connection, which can be represented as a column vector, which is denoted by AWC. Now the loss function for ResNet can be the prediction error, which is like y minus y hat. And the optimization problem for ResNet will be to find the optimal value of the parameters theta Rn, which minimizes the loss function. Next, we can briefly discuss different variants of ResNet, which are dense net, that uses a residual connection in CNN, and neural ODE, which is used for approximating the solutions of ordinary differential equation or ODEs, and ResNet autoencoder, in which the encoder or decoder functions in the autoencoder are replaced using ResNet function. Next, we will be discussing ResNet autoencoder with ordered variants, where we introduce the idea of ordered variants in the ResNet AE. Here is the structure for the ResNet autoencoder with ordered variants, in which we will be using a ResNet connection in the encoder part only, which gives us the latent vector as x plus e of x. And the decoder is a feedforward neural network only. Therefore, in the case of ResNet AEO or RAEO, we have the latent vector y will be equal to x plus e of x, and the reconstructed vector x hat will be d of y. Now we have the unlabeled data set x as in equation 7, and we can define the latent and reconstructed data similar to autoencoder as discussed in the previous lecture, where this latent matrix y contains d samples of the latent vector, and the reconstructed matrix x hat contains d samples of the reconstructed vector. Now using this, we can define the loss function for RAEO as in equation 9, and this is also similar to the AEO as we discussed in the previous lecture. And here we have a reconstructed error term, which is denoted by Jx, a variance regularization term, which is denoted by Jy, and a weight regularization term, which is denoted by J theta. Similar to AEO, in RAEO also we can select these weights Q matrix elements in an increasing order to achieve the latent variances in decreasing order. Now we can split the variables in the input vector to be xp and xr. And similarly, also the latent variables can be split into yp and yr, which was discussed in the previous lecture. But here xp contains the first p variables, xr contains the remaining variables. Similar to AEO, we will be having the variance of the residual variables, or vyr will be equal to 0, since the residual variables having negligible variance. If we substitute this in the encoder equation, we will be having xr plus this function will be equal to 0. Here we have xr is the residual part of the input vector, and this part was similar as the AEO. Here compared to AEO, the only modification is that we have an xr as the additional term. This is because we have used the ResNet connection in the encoder. So therefore our model will be xr plus this term minus yr bar equal to 0, which is in an implicit form. And here we can also try to have an explicit model. And to derive that, we have the first hidden layer of the encoder, F1, as in this equation. And here we have XP and XR is also there. Now, if we retrain this RAEO with A1R equal to 0, which makes the XR will not appearing in this part of the equation, which makes us to write XR in terms of XP by shifting this part to the right hand side, which gives XR will be equal to some function of XP. And this will result in an explicit model. Next, we move on to a numeric example of the RAEO. And here we consider a continuous stirred tank reactor or CSTR process. And here the process is consist of a liquid phase reaction where the liquid A is converted into a liquid B and also a gas C. And this reaction is considered to be an exothermic reaction. Here the dynamic variables in the model consist of the reactor temperature, liquid level, reactor pressure, etc. And the reactor temperature can be regulated using a temperature control system that adjusts the coolant flow rate through the jacket. And the liquid level can be controlled using a level control system that manipulates the outlet flow rate. And the reactor pressure is controlled by adjusting the vent gas flow rate. In this process, we can have around 10 variables, which are denoted by x1 to x10. And the description of the variables are also given, which consist of the reactor concentration, inlet feed temperature, and so on. And we can also have many parameters for which the notations and description are also given here. In the equation 14, we can have a steady state equation for the CSTR process, which consists of 4 nonlinear equations. So here we have 10 variables, which are x1 to x10, and 4 nonlinear equations. Now the dataset for the simulation is generated by using this model. Here we select the first 6 variable and introduce some perturbations in the dataset. And we generate the remaining 4 variables by solving this equation. So that's how we generated all the 10 variables for the training. Then in the simulation, we can select the simulation parameters as in equation 15, where we select the number of layers in the encoder as 2 and also the decoder as 2, and the number of neurons in the hidden layer for the encoder and decoder chosen as 11. Here we can have a performance comparison with the PCA, where we can see that the latent variances are ordered in the case of PCA, but all the 10 latent variances are non-zero, which we can observe from here. Whereas in the case of AEO, the latent variances are ordered, and the last 2 latent variances are exactly 0, and the last 4 latent variances are negligible magnitude. And similarly for RAEO, the latent variances are ordered, and the last 4 latent variances are negligible magnitude. This is particularly because in the original data set, we were having 4 nonlinear relationships, which means the 4 features are redundant. Since the relationships were nonlinear, the PCA was not able to capture the behavior in the latent space. Whereas with the AEO and RAEO, we were able to capture the behavior with 6 features itself. And we were also used it for the model extraction. And here we can see that the MSE for the RAEO and AEO are much small compared to PCA and also the standard AE. Here we plotted X2 versus X9. The original data set is shown in red color, where we can see the data is varying along this range. And X2 versus X9 predicted using PCA is shown in green color. And also X2 versus the predicted X9 using RAEO model is shown in blue color. So here we can see that the blue dots are able to capture the entire trend in the original data set, whereas the PCA based prediction is having only a small range variation. So it's not able to capture the entire trend in the data set. This means that if the original data set is containing a large number of nonlinear relationships, either AEO or RAEO is a better choice for model extraction. And we can also use this extracted model for solving real-time optimization problem. Here we consider the real-time optimization or RTO problem for a CSTR system, in which the objective is to minimize the reactor concentration or X7 in the reactor, which gives us the optimization problem as minimize X7 subjected to the model constraint. Here the RAEO based model is used for defining the equality constraint. We can also set up the minimum and maximum value for all the variables in the dataset. Now by solving this optimization problem, we can obtain the optimal value of the variables or the optimal set point as in equation 70. Normally in real-time optimization problem, we use a first principle-based steady-state model to define this constraint. And if the first principle model is not available, we can use the data-driven models derived using AEO or RAEO to define this equality constraint. That leads us to the end of this lecture. Thanks for watching.